override later on. So all that is that code optimization and that variable, so all of that will be optimized. Another thing as well as talking about this memorize tool. Memorize? Memorize. Okay. That you can actually use it to find the handlers in memory. If you can actually scan, because the handler is going to be something, Temaida, for instance, unpacks all of that in memory. So in Visual Basic, that would be in the DLL and the real code. But if you want to find handlers, you will need to scan memory to actually find all these parts of code, because they might not be referenced directly. After all, they're going to be referenced through a table that the CPU uses. So you can use a tool like that to actually scan for all possible combination of code in the memory you dump to find all these handlers that will give you hints of where those are. But again, this is not like a solved problem at all, and the techniques you can use so far are advanced and somehow primitive, because you're attacking very high levels of abstraction, and but still will be translated to some other representation and do an optimization. If you have different translators for different CPUs, then you would have a common tool that would actually do the optimization for all of those. Like Vorislau their tool did Temaida and did VM Protect more or less generically after some translation, if I remember right. So virtual machines are, I would say, one of the toughest issues right now, just because of the way they obfuscate the code, and there is still no generic way against them. There starts to be some generic approaches, but it's still like reconstructing the flow, which will be one of the more interesting things. Reconstructing the flow of the abstracted application is not obvious, is not doable yet, and it will require a lot of computation, because you really need to go to the level of interpreting every single handler and extracting information from an analysis of that. So it's very computationally intensive. Then, well, I've been talking already quite a bit about this. VM Protect is another packer implementing virtual machines. Armadillo has a different set of techniques that make tracing of application really, really annoying. So all of these, I guess this is needless to say, but all of these are commercial products, and to get to this level of sophistication, you really need to devote some time. So quite often these end up being like full projects, and people make money of them to get to this level of complexity. So I'm going to mention now some of the specific techniques to both Armadillo and Temaida. So one thing, well, Armadillo has one technique that I really like. It has been used as well in other places, but it's this double process debugging. So when you use this kind of protection, Armadillo has a set of protections. But when you use this protection, Armadillo, the packer, is going to run. Then it's going to create another process that is going to create it as being debugged by the first one, by the parent process. So you cannot attach to the child process, because it cannot be attached by two processes at the same time. So the actual application is going to be unpacked in this child process, to which you cannot attach. And and obviously Armadillo is going to do all kinds of checksumming and tests, so the whole thing runs. So that's a nice protection, because either you trace the parent and remove the protection and then go for the child, or you cannot do, or it's a bit hard. And then the nanomice combined with that are extremely interesting, just because it's a way of modifying the flow going back from the parent to the child, and I'm going to detail that in a second. And it's interesting because it breaks the flow in the child, and as well makes the two processes very, very dependent on each other. So you cannot really touch one without, fucking the other. So you really need to be very careful how you play with this. Then another technique that it has is strategic code splicing, just call it like that, which is basically just getting arbitrary chunks of code of the application, putting them somewhere in random memory and executing there. So it's really difficult to dump it properly. I won't go into detail into that one. And one thing that Armadillo does while it's unpacking is throwing all kind of, using all kind of tricks to disturb debuggers. One that you will see is invalid uses of the lock prefix that can bother some virtual environments, just because some of them won't raise an exception for an invalid combination of a lock and an instruction, when a real system should do. And actually, something I noticed when I was playing with Armadillo, and that was a really nice test for WinDebug, was that just after throwing one of these invalid lock combinations, lock instruction combinations, and you have to pass it, if you're debugging this, you have to pass that exception to be handled by Armadillo, otherwise something is going to break. And once that is done, you'll jump into a move. It's like, what could possibly be wrong about the move? So actually, that move that Armadillo was using was an invalid move. Was a move using an invalid combination of operands. So the thing is, it was supposed to throw another invalid opcode exception that was supposed to be handled by Armadillo, but Oli couldn't do that. Oli saw a normal move and couldn't handle that exception, as well as a few other tools that saw that as a move. Was really surprised that WinDebug actually handled that perfectly, recognized it as invalid instruction, didn't disassemble it. So that was a really nice thing for the disassembler. Was aware of that encoding was not valid. All the other disassemblers I tried did say that that was a proper move. And allowed me to actually pass the exception. So with WinDebug, that actually was not a problem to trace through that. But lots of other tools had actually trouble. So it's really nice when you hit something that looks like a roadblock, try different tools, because sometimes it's the tool's limitation when you're working at really, really complex levels or like really advanced techniques. One funny thing, though, is that that was not a problem. The invalid move was not a problem in any of the environments that I run in normally, except in Box. Like VMware, all the others run it and throw the exception properly, but not Box. So I've always wondered, although I asked the guy who brought Armadillo, and he told me he didn't explicitly make that for Box, but I always wondered if it was against Box or some other sort of like full emulator, because a move, you know, it's such a basic instruction that either is executed by the real processor or there has to be some sort of trick with the emulators. Because otherwise, like an Intel processor or most of the virtual machines are going to throw an exception to that, because they will run it natively. There's nothing to it. So it was an interesting case to, you know, make you think of how crazy these guys go to implement all kinds of tricks to break your tools. So now I'll detail a little bit this nanomites thing I talked about. If this unfreezes, come on. Must be because I have pretty pictures on the next page and doesn't want to show them. So, while this decides to pass, oh, nice now. This details a little bit of the nanomites technique. So, to recap a little, the idea is you have a parent process debugging a child process. So you cannot attach to the child. The nanomites, what it does is obfuscates the code a lot by inserting in, for instance, conditional jumps. Instead of the conditional jump in the unpacked application, it would actually insert an interrupt, an int3. The int3, obviously, when it's like reached in the child process, will go to the parent process because it's the one being debugging the child process. What the parent process will do is like it will see where that interrupt was thrown, at which instruction, will look that instruction into a table, then it will look at the E flags to see what condition, what was the condition and where it was supposed to go, whether it's like true or false. And then it will restore the child process with the actual target where it was supposed to go. So when you're actually studying, if you would be studying the child process alone, you will see that it throws an int and eventually appears somewhere else, but you wouldn't see how that flow went there. It's going through the parent that looks it up into a table and then restores the child to be there. So it's like a really interesting interaction between child and parent process. And in the child process, if you would be able to do a dump of the child process, you wouldn't see all the flow, because you could actually end up doing ints for half of the code. So eventually you would have half of the instructions missing that will exist only in the parent, or through the parent, because it will just make you go wherever it wants you to go. So it's a really interesting interaction. And with a tool like Box, it's not a problem to dump and to look into this, because you don't care about who is debugging what. You're at a higher level, or a tool like WinDebug. But if you're with Oli, try this, because you really have to be careful. You have to do it by hand, basically. You have to look at the trick, disable it, and work one and the other. So that's a really good, cute process or technique, these nanomites. Now I'll talk about some of the things that Temida does. One that I really like is how it obfuscates APIs. The algorithm is really interesting, and if you do a dump of Temida, well, if you can, if you can handle that, because they tend to be rather large, you will see that wherever it would, if you use the API obfuscation technique, wherever it would actually call an API function in the original code, it doesn't anymore. It actually calls some code that looks kind of messy. What Temida does, it actually gets the code of the original API in the DLL and reassembles it, inserting a lot of junk in the middle. So it would do the same thing, but it won't be in the DLL. So you won't ever see, if you hook the DLL or something, you won't see a jump to the DLL. It's somewhere else. So, and it will look like crap. So if you try to actually assemble that, you'll see it looks really messy. So the whole process can be like explained visually like this. Normally, the normal relationship between an executable and a DLL is the executable will be importing some symbols, and there will be a set of pointers put towards the DLL function. So whenever a call to whatever imported function is made, it's redirected to the DLL. So specifically in the case of one function, just imagine that exported function from a DLL. Exported functions sometimes, if they do something more than just like setting a value, they are related, they have references to other functions. I'm explaining this because of a technique later. The exported function will reference other functions within the DLL, and that arrow to itself is because it will have conditional jumps pointing within itself and everything. It's a normal function. It will call other things. We will use that in a second. So that would be how it would look, right? So what the metadice is just gets all the exported function and reassembles it somewhere else in the address space of the process, but heavily obfuscated. The thing is, I left those arrows there because the MIDA, I don't know if because of some limitation or because they don't want to go further. It will get really messy if they got further. The conditional jumps, some conditional jumps at least, within the obfuscated DLL still refer the original DLL, and that's something we can use. As well, references, calls to other internal functions within the DLL are kept in place. So if you look at the obfuscated code, if you go step by step and look at all the obfuscated code, you will see that eventually there is a jump that goes back to the DLL, or a call that goes back to the DLL if there is any function from the DLL being used. So that's something that we can use to try to figure out without undoing the obfuscation what actual API was that. So this is basically what I was going to say. This connectivity, the fact that it still refers to parts of the original DLL is something we can use to guess what DLL it was just because of the references. If we study the DLL and see that only one of the calls, exported calls, has the same references, which tends to be the case, then we know that that was the DLL call without actually even looking at the code of the call. So as for the obfuscation, it adds a lot of branching and junk. It's really impressive. As I showed later in that example of Temida, lots of jumps and lots of things that do nothing. Usually, if you're lucky, you see one instruction of the real function per block, but usually there is less than that. There's like one every 3. So one thing is, IDA can easily handle most of the branching, so even if it's obfuscated, you can recover and see most of it, but it breaks whenever you get a call. Because Temida as well, to do all the branching, uses calls that are not real calls, it's just to divert the flow. And IDA tries to assume that that's a function when it's actually not really a function. So IDA will just like break the flow there of the function, but you can actually force it to not do so, and then you will get the whole body. And you could even script this because all of this flow reconstruction is not too hard. What would be a bit harder is the optimization of the call. But if you just want to reconstruct the flow, that can be done. And this is actually how it looks like. This is from kernel 32. This is a get module handle. The one in the right is the original one. The one in the left is the Temida's obfuscated one. It does exactly the same, but with a little bit of messiness on it. And this was using the minimum settings for obfuscation, because I've seen things that wouldn't fit on the screen, like not really small, because it just adds arbitrary amounts of garbage on it. So actually, let me just, because I have this function, just to show you those things I was talking about. So let me see if I have the, yeah, this will be the original one. Let's see if I can. And I will just highlight this location, just remember the 54C. And if I go to the obfuscated one, you'll see like it takes quite a while to get to this part of the code. Again, the movie EDI is in the original function, then starts garbage. All of this is mostly garbage. Follow the jumps, garbage, garbage. Takes quite a while. Every now and then there is like one real instruction, but eventually we'll get to the conditional jump.